Welcome to today's RSECTION training. My name is Sonja von Bloh. I hold the training together with my colleague Richard Hase. He will answer your questions. First, I would like to show you how to use the training interface. The settings allow you to adjust your audio settings. There's also a chat function. You can use the window at the bottom to send us questions or comments. We try to answer these questions within the training. If there are too many questions that cannot be answered today, you will definitely receive an email afterwards. The training is recorded. This will be sent to you after the training. You also get all the models used. This brings me to today's training program. I will first give you an introduction to the section program. Using several examples, I would like to show you the modeling options and design methods in the program. In the first example, a thin-walled eye profile is modeled with graphic functions. I will model this slowly so that you can enter this cross-section as well. In another example, I show you how to insert cross-sections from the database and how you can add other parts to this cross-section. Then I show the modeling of a massive cross-section based on a DXF template. Finally, I model a hybrid cross-section. Then I open RSECTION. RSECTION is an independently executable program for generating any thin-walled or massive profile. If you want to design special profiles in RFEM or RStab that are not contained in the profile library, you can create them with RSECTION. You can then import these user-defined profiles into RFEM or RStab. In RSECTION, it's possible to calculate cross-section values and stresses. The RSECTION user interface is the same like in RFEM 6 or RStab 9. The cross-section graphics and dialogues are displayed in the working window here in the middle. Most tasks can be performed with a mouse. In the tables here below, the keyboard is primarily used for numeric input and output of results. There are 3 navigators in the left pane of the working window. It's the navigator data, the navigator display, and the navigator results. The data navigator manages the input data. A double click on the corresponding entry opens the dialog in which the selected object can be changed. However, it's also possible to create new objects via the navigator data. Just right-click on the object and choose here, for example, new point, and then you can enter the point properties. The display navigator controls the graphical display in the working window. If the checkbox in front of an entry is unchecked, this object is hidden in the graphic. If I uncheck here the points, you see now the points are not displayed anymore. The results navigator controls which results are displayed. You can here switch between the results of the ordinates or the stresses, for example. Then I would like to go into the mouse function. To move the section, you can hold down the mouse wheel, move the section accordingly. You can turn the mouse wheel to zoom, right-click to open the context menu. You can also select objects with the mouse. If you open a window from left to right, everything that's completely within the selection area will be selected. If you drag a window from right to left, everything that is intersected by the selection area will be selected. You can also select individual objects. To do this, left-click on the objects that you want to select. If you want to add objects to the selection, hold down the Control key and then left-click on the corresponding objects. If you want to remove objects from the selection, then hold down the Shift key and click on the objects. This brings me to the first example. To create a custom profile or open the new model window via this button here. First, I have to enter the cross-section name. I name it Example 1. Then I have to define the analysis method. We have two analysis methods available. It's a finite element analysis and the thin word analysis. I choose here the thin word analysis. It's also possible to calculate the effective cross-section. For this, it's necessary to activate this add-on. The effective cross-section can be calculated for both analysis methods. After activating this add-on, a standard must be selected according to whose rules the subpanels are to be generated and the effective cross-section is to be calculated. The following standards are currently available. It's the Eurocode 3 Part 1.1 and the Eurocode 3 Part 1.3 for cold form cross-section and the Eurocode 9 for aluminum cross-section. I choose here the Eurocode 3 Part 1.1. Then I go to the settings and options. Here you have the possibility to define the manufacturing type. The manufacturing type determines which part of the standard is used for the design. For cold formed cross sections, the standard Eurocode 3 Part 1.3 is used, and for hot rolled or welded sections, the standard Eurocode 3 Part 1.1 is used. I don't want to define here the manufacturing type, so I click on OK. Then the new file will be created. I first define the material. A material is already defined, so I double click on this material to open the Edit Material dialog. Here in the list on the left, it's possible to add a new material. It's also possible to copy a selected material or to delete a material. It's possible to enter the material name directly here in this field. Here I enter, for example, an S235, and now our section lists all materials that match that name. But I can also open the material library via this button here for a specific selection. And the material library filters are available to me to quickly find the material. You can filter here, for example, by material name, steel, for example, and you can filter by a standard. There's also a search available where you can enter the material name, for example, S355. I want to use this material, but here from the standard Eurocode 3 Part 1.1. And then I click on OK. If the material is not in the material library, I can create this material by activating here this option User Defined Material. And in the Material Values tab, I can then define the material properties. I don't want to do this today, so I deactivate this checkbox and then I click on OK. I then create the elements. The definition of elements is required if the analysis method, analysis of thin-walled structures, is selected, or if the effective cross-section is to be calculated. An element must always lie in a surface, and the surface is called an R-section part. Elements can be created graphically or via dialog. The graphical input is called up via the symbol in the toolbar, and the input via dialog is called up via the navigator data. Here, new element, single line, for example. When creating an element via the dialog box, the parts and points of the element must be created beforehand, and this is why single line, arc, and so on is deactivated, because we don't have created points and parts and so on before. So I will use here this graphical input. When creating an element via the graphical input, the part is also created. I choose here single, and I want to use the input mode length and direction. I'll enter the bottom flange here first. The bottom flange has a length of 150 millimeters and a thickness of 10.7 millimeter. You can see here a preview of the element, and to create the element, I choose here the desired location, and then I left click with my mouse. Then I define the web, and the web, for this I reverse here the orientation, and the web has an angle in the web plane about 90 degrees and a length about 289.3 millimeters and a thickness of 7.1 millimeter. And then I put this web here in the middle of the first element. Then I create here the upper flange. So I define an angle in the work plane of 0 degree. Length is 75 millimeter. Thickness is 10.7 millimeter. And I choose here this point. Then I reverse the orientation to create the second part, and then I place this here. And with a right mouse click, I leave the window. The profile should be a ruled T profile to which a lower flange is welded. I want to also define here the round radius. So I can define lines to create this round radius, or we have also a function that's called create round corner, and you find here the corresponding button in the bottom. And then you have to define the round radius. This should be 50 millimeters, and all I have to do is to click on the relevant lines. Right mouse click to leave the dialog. Then I want to define the welds. The lower flange is welded with a 6 millimeter double fillet weld, and I create the welds using the create angled corner function. Here you have two corner types. You can define the corner via both edges or via edges and angle, and I choose here edge and angle. It's also possible to calculate in the dialogues, so I define here for the length 6 multiplied by square root from 2, and then I have to define the angle. It's 45 degrees, and click on the relevant lines. What you can now see here, these are the subpanels, and these subpanels are automatically generated based on the standard selected in the base data. If no elements are defined, a cross-section classification in our section and in the design modules of RFEM or RStab is not possible. And neither a calculation of the effective cross-section is possible. In the design add-ons, this profile is then designed according to the cross-section class 3. I would also like to use this example to show you how to calculate stresses and the effective cross-section. In order to calculate stresses or the effective cross-section, a load case must first be created. Load combination can also be formed. So I create a load case first, and I will do this via the navigator data. Here I go to load case, new load case. I name this load case N, and I want to have an additional load case. So I create a new load case and I name this MY. I want to define also a load combination, so I switch to the tab load combination. Here I create a new load combination and I want to assign both load cases to my combination, so I add all. It's also possible here to define a factor. Then I click on OK. Then I have to define the internal forces. The internal forces can be defined manually, or they can be imported from RStab or RFEM. If you want to import these internal forces from RStab or RFEM, you can do this via the table, internal forces, and here you have this function import internal forces from RFEM or RStab. I don't want to import these internal forces. I want to define them manually. So I go to the navigator data again, open internal forces, and then I double click on internal forces for my load case number 1. And here I want to define a compressive force. Compressive forces are negative, tensile forces are positive, so I define minus 10 kilonewton. The axial force acts in the center of gravity of the cross-section. I want to define a bending moment in load case number 2, so I click on apply and next. Then I change my load case to MY. And here I define 0 for the axial force and 100 kilonewton meter for the bending moment. And then I click on OK. If we look into the navigator data, you see now here in load case number 1, we have only defined an axial force about minus 10 kilonewton, and for load case 2, we have an bending moment MY 100 kilonewton meter. The dots that you see now here in the graphics are the stress points. Stresses are calculated and displayed at the stress points. The stress points are generated automatically, but I can also define stress points manually. I want to define the stress points manually, so I go here to the navigator data, and then I open here the stress points. These are the automatically generated stress points, and I want to add a new stress point. So I choose here this option. This stress point should have the number 100, and then I have to define the coordinates. I can define the coordinates manually, or I can select a point in the graphics and import its coordinates. So I want to define it manually. It's 75 millimeter and minus 100 millimeter. And then I click on OK. Now the stress point is created. We can see the stress point here in the graphics. It's also possible to show here the numbering. For this, I go to the navigator display. I activate here this checkbox numbering, and we have here also a checkbox for the stress points. And you now see the stress point number 100. I deactivate this again. Which stresses are to be calculated and output in tabular and graphical form can be set in the stress configuration. I want to show you this now. For this, I go to the navigator data, and here under stresses, stress configuration, I find the stress configuration. The corresponding control fields are to be activated or deactivated here. Now only sigma x total, tau total, and equivalent stress will be calculated. That's okay here in this case. So I start the calculation now. In the results navigator, you can switch between the results of the gross cross-section. These are the thin-walled analysis results, and the results of the effective thin-walled analysis calculation. I show here the results of the gross cross-section first. The same possibilities are included in the tables. Here you can switch between the results of the gross cross-section and the effective cross-section. I choose here the results of the gross cross-section. And it's also possible to switch between the results here of the load cases and the load combination. I look at the load case 1 first, and I want to see here the stresses for load case number 1 for my axial force. It's also possible to change the type of display. I choose here off. And if you want to see the stresses on the stress points that we created, then you can go here to this table, open this tab, all stresses by stress points, and if you choose this stress point, then you go directly here to the stress point in the table. It's also possible to show the statical moments as y SZ and so on. We have the statical moments also in the table. Here, statical moments and warping. I want to go to the effective cross-section results now. So I change here in the navigator results effective thin wall analysis, and I want to see here the stresses for load case number 1. I change this here also in the table. You see here the section property of the effective cross-section in comparison to the section properties of the gross cross-section. The section property of the effective cross-section are reduced. You can see here graphically that in load case number 1, the web falls into cross-section class 4. Local buckling occurs in class 4 cross-section. According to the standard, the reduction in strength due to local buckling can be taken into account through effective widths, and this is calculated automatically here in our section. You can see here the section classification also in the table. You see here, okay, classification, this cross-section falls into class 4. And if you click on the subpanel of the web, you see here the details of the classification. And it's also possible to see here the effective width of this subpanel. Here if I switch to the bending moment and go here to the section classification, you can see this cross-section falls into class 1, so no reduction has to be made. And for the combination, I see that this cross-section falls also in class 1. I would now like to use another example to show you how you can access cross-sections from the library and modify them. For this, I create a new file via this button. I call it example 2. Here I choose the analysis method thin-walled analysis, and I want to calculate also the effective cross-section. So I activate this checkbox and I choose the standard Eurocode 3 part 11. And then I click on OK to create this file. I then define the material. This should be in S235. So I open here the material library. I type the material name S235 from this standard OK. And then I insert a cross-section from the cross-section library. To do this, I go here to the navigator data and open here the window new section. The window is structured like the material window. A cross-section can be created or copied via the list here, via these buttons. I can enter also here the cross-section name, for example, IPE 200. but it's also possible to open the cross-section library via this button. A large number of profiles have already been entered into the profile library, and I want to choose here a standardized L profile, and name is L200 150 12. I choose here the standard, then I click on OK. The angle should be mirrored around the y-axis, so I activate this checkbox, and the angle should be also rotated about the x-axis, about 90 degrees. Furthermore, I select the offset point in the graphic, and at this point the profile is placed at the insertion point. I pick for this point here, and then I define the insertion point. I can pick this also graphically here in the working window, and then I click on OK. When inserting this thin-walled cross-section, two elements are defined and one part will be created. The cross-section can be subsequently edited, moved, mirrored, or rotated. You can open here this dialog, or you can use here this function for move copy or rotate and so on. However, in order to modify individual objects such as points or lines, the cross-section must be splitted. The cross-section is to be supplemented by further cross-section parts. I therefore split the cross-section into its individual parts for further processing. To do this, I right-click on this section, and then I choose here Explode. The fillet isn't needed, so I delete this. So I choose here this point and click on delete. Now the part is deleted too. I also add more elements. I insert an element with a thickness of 12 millimeter and a length of 200 millimeter, and I will do this via the graphical input. Here I choose single. I choose the input mode length and direction, and I reverse the orientation, and the length should be 200 millimeter, thickness is 12 millimeter, and then I put this element here. I want to add another element for the web with a thickness of 10 millimeter and a length of 400 millimeter. For this, I define here an angle on the work plane. I have to reverse the orientation. Length should be 400 millimeter, thickness 10 millimeter, and I create this element on this position. I now delete unnecessary lines. I don't need this line, and I also don't need this line. And welding seams should also be taken into account. so I create the welds using the function create angle corner. Here I use the corner type edge and angle, and a double fillet weld is to be defined, so that I define here 6 multiplied by square root of 2 with an angle of 45 degrees. And I define it here on these positions. Furthermore, I still have to create the part by selecting here this function select boundary. Here I have to choose the material, and then I click on the line, and now the part is created automatically. I would now like to calculate the effective cross-section and the stresses, so that I create a new load case. So for this, I create a new load case. I call this load case N, and a second load case My. I want to create also a load combination with N plus My, and I click on OK. Then I have to define the internal forces. For this, I open here the internal forces, and in load case number 1, I create an internal force about -50 kilonewton, apply a next, change the load case. Here, axial force should be 0 and My should be 20 kilonewton meter. Then I click on OK. I start the calculation now. And I look at the effective of the result of the effective cross section. For load case number 1, I see here a reduction in the web and in the flange. And if we look here on the section classification, you can see this cross section falls into class 4 for load case number 1, and also for load case number 2, but here only the flange is reduced. We can change here also the type of display to off, and then we look to the classification of the load combination, and also for the load combination, this cross section falls into class 4. I want to create the documentation now, and the documentation is done in the printout report. And for this, I go to the navigator data again. And here I create then the new printout report. Here I can choose the report items that should be included in the printout report. I don't want to have here the stresses by loading and material and so on. So I click now here on Save and Show. Now the printout is created. We have here now the tables that we have chosen in this printout report manager. And it's also possible to print a graphic to this printout report. I want to show you this now. And to print this graphic to the printout report, I choose here this function, print graphics to the printout report. Here you have the possibility to make various settings. You can define here the graphic printed that it's window filling, and you see here this in the preview. Then I go to save and show, and now this graphic is printed to the printout report. In the next example, I would like to show you that you can also create cross-sections by importing a DXF file. Now I close this printout. A DXF file can be imported via menu File, Import DXF. Then I choose here the corresponding DXF file and click on Open. I don't want to import this DXF file into the active model. I want to create a new model, so I click here on No. In the section Create RSECTION Model, you have 3 options for creating the cross-section. The automatic creation of elements is useful if the outlines of the cross-section are available in the DXF file. RSECTION attempts to create setter lines for parallel lines and then set the elements between the intersections. Only elements that do not exceed the maximum thickness defined here in this maximum thickness field are created. The import function use DXF template lines as center lines is useful if the cross-section geometry is available as a centerline model. The lines of the DXF template are considered as the center lines of the elements. The thickness defined here in this field T is assigned equally to all elements. The function create DXF template is useful for massive cross-sections where no elements needs to be created. In addition, this function can also be used for complex cross-sections where I only want to create elements for the decisive cross-section parts. With this import function, the lines in the DXF file are imported as lines. You can then use these lines as an aid for modeling. I use this function today, so I click here on OK. Now the lines are created. A finite element analysis is to be carried out on the imported profile. I set this in the base data. For this, I open here the base data. This is already chosen. A finite element analysis should be performed on massive cross-sections, such as timber cross-sections or concrete cross-sections, in contrast to thin-walled cross-sections, where the stresses can be regarded as constant across a cross-section thickness. The stress distribution in solid cross-sections is variable. This can only be determined with a finite element analysis. So I click here on OK. Then I have to define the material. This should be an aluminum material. So I modify this material. I open the material database. I choose here the filter aluminum, and this should be a 6060 aluminum material. Here, this material, OK, and then OK. In a finite element analysis, only a surface needs to be defined, but no elements needs to be defined. I would only have to define elements if I also want to calculate the effective cross-section or carry out a classification. So I only have to create a part here, and I create this part via the function select boundary. Then I click on the outline and the part is now created. After creating the part, I still need to create the openings. For this, I use this function select boundary for openings, and then I click here on the relevant line. I want to show you that you can also create openings via rotating them. So I select here this opening, and then I open the function rotate selected objects. Here I want to create a copy. I want to create 3 copies. Rotation angle is 90 degrees, and the point of rotation is here in the middle. Then I click on OK, and now the openings are created. I still need an opening here in the middle. So for this, I use this function select boundary again. And now the cross-section is complete. I want to calculate the stresses here as well. So I create a load case, new load case, and I name this load case n plus mxp. And then I click here on OK. Then I define the internal forces in the load case. And internal force should be axial force about minus 10 kilonewton and a torsional moment of 0.3 kilonewton meter. And I click on OK. Then I start the calculation. And now I look onto the results. I want to see here the stresses, sigma x, and here also the shear stresses. And I look here also on the stresses, sigma equivalent. I want to create a printout, and I want to include also this graphic. So I create a printout first. I go to this navigator data. Then I right click on printout, new printout. I select here the relevant items. Then I click on save and show. And I want to add this result graphic to the printout report. So I choose here print graphics to the printout report. Save and show. And now this graphic is also printed to this printout report. As a last example, I show the modeling of a composite cross-section. In our section, it's also possible to model cross-sections that consist of different materials. Ideal cross-section values are determined for such a cross-section. For this, I create a new file. I name it hybrid. 1,000 millimeter wide and 200 millimeter high concrete cross-section lying on an HEB steel cross-section is to be modeled. So I choose for this the analysis method finite element analysis. Then I click on OK. I define 2 materials. For this, I open here the edit material dialog. First, I define the material for the concrete part of the cross-section. I open here the material library and I search for C4050 from the standard. Okay, then I need an additional material for the steel cross section, so I create a new material, open the material library, and this should be S235. Then I click on OK and OK. First, I model the concrete cross section. For this, I use a cross section from the library. So I choose here new section. Geometry B is 1000 millimeter, H 200 millimeter, and then I click on OK. Then I create my steel cross section. This is also included in the section library. So I create here a new section, open the section library, open here the I-beams, and here I look for an HEB 400, and material for this cross section should be S235. I choose the center of the top flange as the offset point, and I choose here the bottom of the concrete cross section as the insertion point. Then I click on OK. I now create a load case because I want to also calculate the stresses. So new load case, I name it M. And in this load case, I define my internal forces, and this should be a bending moment only, My 100 kilonewton meter. I start the calculation now, and here the stresses are calculated, section properties, and so on. I would also like to show you how to import the cross-section into RFEM. To do this, I save the cross-section first, and then I open RFEM. I've already created a file. Then I have to import this cross-section. To do this, I go to the navigator data, sections, new section, open the cross-section library, section from R section, and then I choose here this hybrid cross-section. You see now the option hybrid is activated. I have also a tab for this material assignment, and I now see which materials are assigned to the cross-section parts. I see here also the reference material. It's also possible to define a different material here. Then I click on OK, and then I can use this cross-section. I can create a new member with this cross-section, and I can use this in my static analysis. With this example, I have come to the end of the training. It was taught how you can create general cross-sections with graphic functions, how you can add cross-section parts to database profiles and create profiles based on a DXF import. Finally, I would like to point out our career page. For this, I open here my presentation again. You find a link to our career page in the presentation. If you are interested, please send us your application. I hope that the training for using RSECTION has helped you, and thank you for your attention.